In this example, we'll practice calculating the moment about a point on a rigid body that are applied due to external forces. So here we see a simple model of a vibration isolation table. And these isolation tables are used to set equipment on that can't experience any vibrations to work correctly. So we see that this is a 2 degree of freedom system. We have a vertical translation, and then there's a single rotation out of the plane. And because there's one rotational degree of freedom, that means we need 2 reference frames. So we'll apply an inertial reference frame where we have 3 basis vectors, E1, E2, and E3. And E1 is defined as along AB when theta is equal to 0. E3 is out of the plane, and then E2 is the cross product between E3 and E1. Then we'll apply a body frame that's attached to the table. Its basis vectors are B1, B2, and B3 with an origin at the center of mass. B1 is along AB, B3 the same direction as E3, and then B2 is the cross product of B3 and B1. And then to finish the relationship between these reference frames, we have the angular velocity of frame B as observed in frame I is equal to theta dot in the B3 direction, and then we have our transformation table between the 2 bases. To calculate the moments that are applied to the table, we first need to draw a free body diagram of the table and apply each of the forces. And so our spring forces are acting only in the vertical direction. So we have a spring force at A, so F sub S A. We also have a spring force at point B, so F sub S B. And then we have the force due to gravity, which is located at the center of mass, which is mg in the negative E2 direction. And so we have all of our forces represented as vectors that are applied to the free body diagram, and then the table itself is a length L. And so now let's define our spring forces in the basis vectors that we have. So take the spring force at A. Our model for this is negative K, spring coefficient, of L minus L naught, where we have the length of the spring minus the resting length, and this is in the US direction. And in this model, US is defined as the direction from the attachment point off the rigid body to the attachment point of the spring on the rigid body. Let's define each of these components. U sub S is in the E2 direction because the attachment point off the rigid body is below, and then on the rigid body A is above that, so E2 is pointing up. And then the length of our spring, L, will be the norm of R, A with respect to O, dotted with US. And then our resting length, L naught, is Y sub A. Our position vector, R of A with respect to O, is equal to Y in the E2 direction, so we're going from point O up to G, so that takes us to Y in the E2 direction, and then we're going to go to point A, which is negative L over 2 in the B1 direction. The length of the spring is the norm of this vector, Y in the E2 direction, minus L over 2 in the B1 direction. We're going to dot that with U sub S, but we've defined U sub S as E2. So we're dotting this with E2, and then finding the magnitude by taking the norm. And so in our dot product, we see that Y dotted with E2, Y E2 dotted with E2 gives us Y, but then we have to do a dot product of L over 2 B1 with E2. And the easiest way to do that is by looking at the transformation table, where we have B1 dotted with E2 is equal to sine theta. So this becomes our magnitude minus L over 2 sine theta. And then we substitute in each of our pieces, and we get the vector F sub S, the spring force attached at A, is negative K sub A. this is the spring coefficient for that spring, multiplied times y minus L over 2 sine theta minus y sub a, the resting length of the spring, and this is in the E2 direction. We go through a similar process for the force due to the spring located at B. So this is equal to negative K, L minus L naught, and this is in the U sub S direction for B. U sub S is equal to E2 again. We have that L is equal to the norm of RB with respect to O, dotted with US, and then L naught is equal to Y sub B. And by going through the same process, we find that the force at spring B is equal to negative K sub B, and it's Y plus L over 2 sine theta minus Y sub B. And so finally we calculate our moment. And the moment about the center of mass will be the position vector of A with respect to G crossed with the force at A, so that's our spring force at A. We're going to add to that R of B with respect to G crossed with our spring force at B, and then add to that the last force, R of G with respect to G crossed with negative mg in the E2 direction. Of course, we can see that the position vector of G with respect to G is 0, and so because we're taking our moments about the center of mass, then this last term will be 0. We need to define each of the terms present here. So we have our spring forces, our force at A and our force at B, and then our position vectors we'll define as R A with respect to G is negative L over 2 in the B1 direction, and our position vector of B with respect to G is equal to positive L over 2 in the B1 direction. And so the moment about the center of mass is equal to negative L over 2 B1 crossed with the expression negative K sub A Y minus L over 2 sine theta minus Y sub A, that's in the E2 direction, and then we'll add to that the term L over 2 B sub 1 crossing this with negative K sub B Y plus L over 2 sine theta minus Y sub B in the E2 direction. And so then after evaluating the cross products, we get that the moment about the center of mass is equal to Ka L over 2 multiplied times the quantity Y minus L over 2 sine theta minus Y sub A. This is in the E3 direction. We have another E3 term, so it's minus K sub B L over 2 Y plus L over 2 sine theta minus Y sub B. So this is also in the E3 direction. And so here, this is the first time that we've calculated moments, and these are dynamic moments. So notice that the moment is going to change based on theta and based on y. So we have both of our degrees of freedom here. We have both of our coordinates that'll change. So as the table translates up and down for y, the moments will change, as well as the moments will change as it rotates.